Okay, so uh, announcement before we get started. Of course, our exam begins on Friday and goes Friday through Monday in the testing center. Usually before exams, I like to hold review sessions. The university is not allowing us to hold in-person review sessions this semester. So what we will do instead is tomorrow I will be filming a review session where I'm basically just going to outline the 4 chapters that we are studying in this section of the class, focusing on the key topics of each chapter, and then telling you what sorts of skills you'll need to have related to each of those topics, what sorts of problems you would need to be able to solve. And I'll also talk a little bit about the exam in general on that. And then we'll post that on YouTube, and the link will be on Learning Suite, just like for the classes that we're filming. And so hopefully we'll have that posted by the late afternoon or early evening of tomorrow. And then you should watch that. And on Thursday evening, when I would normally do an in-person review session, what I will do is a Zoom question and answer session. I'll send out the Zoom link later in the week. But from 7 to 8 o'clock Thursday evening, I'll be available on Zoom, and you can ask me questions about the topics, the problems. So it would be much more effective if you'd been able to watch that review session prior to the Zoom question and answer session. So that's how we're going to handle reviewing for the exams in this era of COVID. So today, we have one more interesting molecule from chapter 3 to talk about, and then we're going to go into chapter 4, and we're going to learn about alkanes and cycloalkanes. These molecules are unreactive. They don't have functional groups. We learned that in chapter 3. So we're not going to learn about reactions in this chapter. What we're going to do is use alkanes and cycloalkanes as a way of learning 2 topics. One is nomenclature, or how to name organic compounds. The other one is conformational analysis, or how to study their 3-dimensional structures. Okay? But before we get to that, let's talk a bit about amphotericin B. Amphotericin B is a very large molecule. It has a 38-membered ring. It is an antifungal agent, and we'll talk a little bit about why its structure makes it an effective antifungal agent. So amphoteric means having acidic and basic functional groups. We have a carboxylic acid and we have an amine, so we do indeed have an acidic and basic functional group. But what makes it effective as an antifungal agent is the fact that it's amphiphilic. We learned the definition of that last week. So it really should be called amphiphilicin. If I would have named it, I would have called it amphiphilicin. But they call it amphotericin instead. So you'll notice that we have all of these carbon-carbon double bonds, right? Alternating carbon-carbon double and single bonds here in this region of the molecule. And that's absolutely critical to the 3-dimensional structure of amphotericin and to its activity as an antifungal agent. Okay? So if we look, sorry, this got turned off, or maybe the battery died. There we go. If we look at the shape here on the screen, we see that it is elongated. It's a long cylindrical molecule. It's not a circular ring. And that's due to the presence of these double bonds here. Okay? These double bonds elongate the structure and make it long and thin and cylindrical instead of more spherical or circular. And you see that we have 2 faces to the molecule. We have this bottom face, the way it was drawn here, and this is a low resolution picture. I couldn't get a digital copy of this. I had to photocopy it from a book and cut and paste it into this document, which is why it's kind of grainy. But it's good enough for what we need to see. We see that we have the bottom face of this molecule is very, very nonpolar. It only has carbon-carbon and carbon-hydrogen bonds. And then we see the top face of the molecule is very polar. That's where all of these OH groups reside. Okay, so we have a lot of polar functional groups capable of hydrogen bonding. We have this ester functional group. So we have the polar face that is capable of hydrogen bonding, the nonpolar face that is only capable of having van der Waals forces with other molecules. We do have a polar head group here. That polar head group will be important as we see in a moment, but the main features are these two polar and nonpolar faces. So we have another low resolution figure. Again, it comes from a book that I had to photocopy it out of, but it's going to be high enough resolution for us to see why amphotericin B is effective as an antifungal agent. That elongated cylindrical structure is key because the molecule is long enough to span the cell membrane. So what happens is a molecule of amphotericin B can insert itself into the cell membrane, and you're going to have the polar head group on the outside, of course, and you're going to have the nonpolar face facing the nonpolar molecules inside the lipid bilayer. Of course, you have the tails of the phospholipids. You also have, in mammalian cells, cholesterol, which is a very nonpolar molecule. And in fungal cells, you have a molecule that's similar but not identical to cholesterol called ergosterol. And so this figure shows amphotericin B stacking with a molecule of ergosterol being held together by van der Waals forces because we have a nonpolar ergosterol molecule, and then we have the nonpolar face of the amphotericin B. Now, the polar face would have nothing to interact with except for the fact that two molecules of amphotericin B are going to insert into a cell membrane at a certain location, and that allows the two polar faces to hydrogen bond to each other. And so you're going to have stabilizing non-covalent forces between two amphotericin molecules at those polar faces. Okay? And then the other face of that second molecule is going to have van der Waals forces attracting it to another molecule of ergosterol. Okay? So what this does is it forms an artificial channel or an artificial pore in the cell membrane. This region in between these two amphotericin molecules where we have these hydrogen bonds is not impermeable, right? It's leaky. Water can flow through it. And if water can flow through it, then cations can flow through it because the cations are dissolved in water. So now you have unregulated flow of cations in and out of the cell, and that's what kills the cell, okay? Similar to what monensin does, what we talked about on Friday, except instead of carrying the molecules across the membrane, what amphotericin B does is create an artificial hole or pore in the membrane, allowing the cations to flow in and out, okay? So it's just the right size to do this, and it also has this amphiphilic property, this polar face and this nonpolar face. It's those structural features that allow amphotericin to kill fungal cells. Question? Yes. Yeah, it's going to elongate the structure. It's going to make it harder. If you make a molecular model, you'll find that those double bonds make it more rigid and make it harder to twist around and become more of a circle. So yes, the double bonds cause it to be elongated. You might wonder, why does it not kill human cells? It does, just not as effectively as it kills fungal cells. So a physician would have to get the dosage just right if you had a severe fungal infection to give it to you so it would kill the fungus and not kill you. But the reason, we're not going to go into the molecular basis, the reason is that fungal cells have ergosterol, human and mammalian cells have cholesterol, and it turns out that the van der Waals forces between amphotericin B and ergosterol are stronger than they are between amphotericin B and cholesterol. So it prefers to insert into fungal membranes. So very, very well designed molecule by nature. Questions? All right, so we have a lot of interesting molecules we learned about in chapter 3. I told you chapter 3 was one of my favorites because we get to talk about these compounds and talk about how they work and why they do the jobs that they do. And we're going to pivot from that to, frankly, one of the most boring topics of the semester. Okay, I hate to say that, but it's true. So today we're going to learn how to name alkanes, which tells us nothing about their function and their chemistry. So it's not terribly exciting, but it is necessary, right? We wouldn't do anything in class that's unnecessary. It is necessary for us to learn how to name alkanes and cycloalkanes. but we're going to learn just enough. We're going to learn just what we need to know and nothing more in terms of nomenclature because it's not a very exciting topic. Okay, but to start out, so our alkanes, no functional groups, sp3 carbons. So we have tetrahedral geometry at all of the carbons in our alkanes. They can be divided into two types. The first type is acyclic alkanes. These are alkanes that are chains. The other type, which we'll discuss in a moment, are cyclic alkanes. They have rings, or cycloalkanes. So alkanes, acyclic alkanes have the general formula shown here, meaning that for every n carbons in the molecule, you will have 2n plus 2 hydrogens. They're referred to as saturated hydrocarbons, meaning that they are saturated with hydrogens. They have the maximum amount of hydrogens that you can have for this number of carbons. We'll learn a little more about unsaturated hydrocarbons that don't have that maximum amount of hydrogen shortly. So the simplest acyclic alkane is just CH4, that is methane, or natural gas, the main component of natural gas. C2H6, which I've drawn for you here, is ethane. That is a minor component of natural gas. And then we have C3H8, which is propane. Propane can be liquefied under pressure. And so if you have a gas grill, you'll have a propane tank containing propane. That's what's used to fuel gas grills. And for cabins or homes in rural areas where there's no natural gas pipeline or delivery, then those homes or cabins will have big giant propane tanks out back that will power any kind of gas-powered appliances such as a stove or a hot water heater. Okay, so that's what these simple acyclic alkanes are used for. Now, when we go from 3 carbons to 4 carbons, now there's two different ways we can connect those 4 carbons together. We can put them in a straight chain, and we refer to that as butane. But we could also have a 3-carbon chain with a 1-carbon branch coming off of the middle carbon. That is an isomer of butane, so that is referred to as isobutane. Okay. Which one would have the higher boiling point, butane or isobutane? Butane has the higher boiling point, more surface area. So the boiling point of butane is slightly less than 0 degrees. You have to cool it down below the temperature of ice in order to get it to liquefy. And then isobutane, minus 10.2. Okay? Butane is actually the fuel that's used in lighters. Right? Any kind of lighter, like a cigarette lighter or a lighter for a grill, would have butane inside. Okay? All right, what kind of isomers are these? Constitutional isomers. Yes, those are constitutional isomers. Okay? So before we describe larger alkanes, question? Molecules with the same molecular formula, but a different connectivity of the atoms. There are other types of isomers we will learn in this chapter. So we have isomers, which is same molecular formula but different compound. That's going to be divided into different types of isomers. The only one we've learned so far is constitutional isomers. So you may be thinking that every isomer is a constitutional isomer. To this point in the class, that's correct. But after either the end of class Wednesday or early on Friday, we'll introduce a second type of isomer, which is a stereoisomer. All right. So some vocabulary that we need to learn before we can discuss larger alkanes. And that's referring to types of carbons or the degrees of carbons. Okay? So we can have a primary carbon. A primary carbon is bonded to one other carbon atom. And based on this definition, we can define, secondary, tertiary, and quaternary carbons. Secondary carbon is going to be bonded to two other carbon atoms. Tertiary carbon bonded to three other carbon atoms. So we're going to have less hydrogens attached as we go from primary to secondary to tertiary. And then we have a quaternary carbon, which is bonded to four other carbon atoms and would have no hydrogens attached. Okay. So in butane, what kind of carbon is the one I'm pointing at right here? That's primary. What about this one? That's a secondary carbon, exactly. In isobutane, what kind of carbon is this? That's a tertiary carbon, bonded to three other carbons, has one hydrogen attached, okay? And then this molecule here, that central carbon, what kind of carbon is that? That's a quaternary carbon, okay? We can also refer to hydrogens by this nomenclature. There's no such thing as a quaternary hydrogen because there's no hydrogens on a quaternary carbon, but a primary hydrogen would be attached to a primary carbon and so forth. Okay. And then some other nomenclature, other definitions, I should say, that we need to learn. Still haven't figured out the raising of the board here very well. Okay. So these terms are not specifically defined in your book, but they're important to learn. When we have a CH3 group, and it's obviously going to be attached to one other thing, it could be attached to another carbon, could be attached to an oxygen, a chlorine. We refer to that as a methyl group. Okay. And then we can have CH2. That's going to be attached to two other things, two other carbons, a carbon and an oxygen. That's referred to as a methylene group. And then we can have a CH. That's going to be attached to three other things, three carbons, two carbons and an oxygen, various different choices. That's going to be referred to as a methine group. Okay? So this is some vocabulary we need to know in order to name and discuss organic compounds. Okay? All right, so let's take a look at a table from chapter 4. And this table shows us number of carbon atoms in a chain. It doesn't have to be a straight chain. Molecular formula, a name, and then when it says N-alkane, that's the name for the straight chain with that formula. And then over here we have number of constitutional isomers. Okay? So we went up to butane. We didn't do the isomers of pentane or hexane. You can see that the numbers escalate pretty quickly. There's no formula that allows you to figure this out, these numbers, so we're not going to really be worried about that too much. Just note that the number of constitutional isomers does go up quite a bit as you add additional carbons. But the important thing about this table are these names, okay? So 1 through 10, we need to memorize the names for the straight chain alkanes from 1 through 10. Right, from 5 onward, it's based on the actual numbers themselves, right? Pentane, hexane, heptane, so they're pretty easy. And we don't need to go beyond 10, but we do need to memorize these names, okay? So, questions on alkanes. We'll talk a little more on naming alkanes, but let's talk about cycloalkanes for a moment. So a cycloalkane will have a ring as opposed to a straight chain. And it has a different formula. A cycloalkane will just have twice as many hydrogens as it does carbons. That's due to the fact that if you're making a ring from a straight chain, you would have to remove a hydrogen from each of the carbons on the end in order to form a carbon-carbon bond to link those together. So in a cycloalkane, we have a carbon-carbon bond in place of 2 carbon-hydrogen bonds. So we have 2 less hydrogens per the number of carbons. So cycloalkanes would be unsaturated, where acyclic alkanes are saturated hydrocarbons. Cycloalkanes would be unsaturated. And the way we name cycloalkanes is very simple. We just add the prefix cyclo to the name we get from this table. So what's the name of our smallest cycloalkane? Cyclopropane, exactly. 3-membered ring, that's the smallest one we can have. We'll learn more about it on Wednesday. This is our most common one, our most important cycloalkane. What do we call that? Cyclohexane. We're going to spend a lot of time on Friday talking about cyclohexane. Okay? All right, any questions on how we name cycloalkanes? Question? The what? What was that? A phenyl group? Phenyl is not the same as cyclohexane because phenyl has double bonds in it. Okay? This has no double bonds. So as far as the properties of cycloalkanes, we'll learn more about those at the end of class on Wednesday and Friday. But what I'll tell you now, a key difference between acyclic alkanes and cycloalkanes is the former have free rotation about all the carbon-carbon sigma bonds. You can rotate 360 degrees about any of the sigma bonds in an acyclic alkane. In contrast, in a cycloalkane, you can twist a little bit about the bonds, but you cannot rotate 360 degrees. Otherwise, you'd break the ring. Okay? If you don't have a set of molecular models, I encourage you to get a set of molecular models. You'll be able to use them on the exam. They'll be very helpful to you on the exam and in the homework. They can be a very simple set. As long as you can make a 6-membered ring with 3 different groups coming off, that's going to be a good enough set of models for you to use. But if you make a ring and you try to rotate 360 degrees, you're going to break the ring. That's a sign. That would happen in nature as well. So that's a sign that you don't have free rotation in cycloalkanes, you have restricted rotation. Okay? And that makes a difference in their properties. Okay, so let's talk a little bit about how we would name acyclic alkanes. We know how to name the straight chains, but how do we name them when branches come off of the chains? In order to name the branches, we have to learn about alkyl groups. Okay? So alkyl groups are simply acyclic alkanes where we've removed one of the hydrogens and we've used that missing valence to attach the group to a longer chain or to a ring. And I've already taught you one alkyl group. It's sitting right here. Okay? CH3, that's a methyl group. And the way we come up with a name for alkyl groups is very simple. We drop the ane from the name in this table, and we add YL. So this is a methyl group. When we have a CH3 hanging off of a longer chain or hanging off of a ring, we call that a methyl group. This squiggly line indicates the point of attachment. So this is ethane, where we've taken off one of the hydrogens, and we've used this bond that I've drawn the squiggly line through to attach that to a longer chain or to a ring. What would we call this alkyl group? 2-carbon alkyl group. What would we call it? Yes? When we get the answer, it might become more apparent. So if someone knows the answer, yes? Ethyl. So that's an ethyl group. So what we have here We have a carbon, that's a CH3. We have a carbon there, that's a CH2. And the bond I've drawn the squiggly line through, that means that that CH2 is attached to something longer, either a longer chain or to a ring. Yeah, something else. Okay, so methyl and ethyl, those are our simplest alkyl groups. My grandfather was an organic chemist. That's how I got interested in organic chemistry myself. And he said that if he ever had twin daughters, he would have named them Methyl and Ethel. Fortunately, that didn't happen. I love organic chemistry, but I would never name a child after an alkyl group. I think that would be a punishment. So, all right, 3 carbons. If we take propane and we take off one of the hydrogens from a carbon at the end of propane and we attach it to something else, what would we get? What would we call this based on the pattern we've learned? That would be propyl. But the challenge we face with propane is that propane itself has 2 types of carbons. It has primary carbons on each end, and it has a secondary carbon in the middle. So we can take off a primary carbon, and we can attach that 3-carbon unit to a longer chain or to a ring, and that's a propyl group. But we could also take off one of our secondary carbons, and we could form a bond, or one of our secondary hydrogens, and we could form a bond from that secondary carbon to a longer chain or to a ring. So we need to have a name for this one. We call that isopropyl. Okay? So we have propyl and isopropyl. Now it gets better when we get to 4 carbons, because we now have 2 isomers with 4 carbons, butane and isobutane. So we could make alkyl groups based on butane, and we could make alkyl groups based on isobutane. So let's start with butane. What do you think we call this one? That one's called butyl. Okay? But we could attach this 4-carbon group from a secondary carbon, and we call that sec-butyl, where the sec just is short for secondary. Right? So sec-butyl is the 4-carbon straight chain attached at the secondary carbon. Now let's look at isobutane. And if we remove one of the primary hydrogens from isobutane and attach to our longer chain or to our ring, we get an isobutyl group. Okay? But in isobutane, over here, we have a tertiary hydrogen. So we could take off that tertiary hydrogen, and we could attach this tertiary carbon to a chain or a ring, and that's referred to as tert-butyl, where the tert refers to tertiary. Okay? So 4 different types of alkyl groups with 4 carbons. I've explained to you how the names are derived. If you learn how the names are derived, it's not as much of a straight memorization to get these names right, but you do have to memorize these names. You do have to know the names and the structures of these alkyl groups. Any questions on how we derive these names and what they refer to? Yes? It was a tertiary carbon in isobutane. When you attach it to something, it does become a quaternary carbon. You're exactly right. But when we remove a hydrogen from isobutane and turn this into an alkyl group, it was a tertiary hydrogen we removed. So that's why it's called tert-butyl. This is isobutane. This is a tertiary carbon. How many hydrogens are on that carbon? 1. If we remove that hydrogen and we attach that carbon that we removed the hydrogen from to a longer chain, that's a tert-butyl group. So we've removed a tertiary hydrogen to create that alkyl group. Correct. It came from a tertiary carbon. Good. Other question? Yes, except for isobutyl. Isobutyl is just the parent, the primary carbon of isobutane, right? Okay. Yeah, it has the name of the parent alkane if it is the primary carbon. So the parent alkane of these two is butane, and we put the sec in front when we detach the carbon, a hydrogen from the secondary carbon. And then the parent alkane here is isobutane. We put tert in front when we detach the hydrogen from the tertiary carbon. One other thing to remember on these names, sec and tert are italicized, and they have a little hyphen. Iso is not italicized and has no hyphen. Okay? I didn't make up these rules, I'm just teaching them to you. So it's not my fault that they're confusing. I apologize. The good news is we are not naming any more alkyl groups. We're only going up to 4 carbons. Okay? We're not encountering any alkyl groups longer than 4 carbons. One thing I'll tell you about naming organic compounds is you can go into it in as great of depth as you would like. You can always draw a more complicated molecule and figure out how to name it. But I would urge you not to do that because that's really a waste of your time. Because as I mentioned, that doesn't tell you anything about the properties of the compound. The most exciting thing about organic chemistry are the properties of the molecules, how they react, what they're used for, not how you name them. And so I would urge you to not go any deeper on nomenclature, to not play what I like to call the what if game. Well, what if I had this group, that group, 3 groups, 5 groups? Just don't ask those questions. Only focus on naming the compounds, the simple compounds we'll encounter in class, because that's all you'll need to name on exams and quizzes and homework. Good, I'm glad you approve. All right, so now let's discuss how to name how to name an acyclic alkane. We're going to go through a 4-step process. I can still see the outline of the molecule I drew on the board in the last hour. So I'll just redraw it. We're going to name this compound right here. And we're going to go through a 4-step process. And this is known as IUPAC nomenclature, by the way. Okay? So IUPAC nomenclature is a systematic way of naming organic compounds. IUPAC is the International Union of Pure and Applied Chemistry. It's the worldwide governing body of chemistry. You might wonder what they do, other than sit around and think they're important. Well, whenever we need some sort of a worldwide system for something in chemistry, that's what they do. They come up with those sorts of things. They also sponsor worldwide chemistry meetings when we're able to have meetings. But one of the things they've done is they've come up with a worldwide system for naming organic compounds so that everybody around the world names them the same way. And that name has 3 components: a prefix plus the parent plus the suffix. Okay? The prefix is going to tell us about substituents. Substituents are groups that are coming off of chains or rings. It's going to tell us what kinds of substituents, how many substituents, and where they're located. The parent tells you the number of carbons in the ring or the chain. And that's going to come from our table here. And the suffix is going to tell you the type of the compound or what functional groups are present. The suffix for all the molecules in this chapter will be ane, which indicates that it's either an alkane or a cycloalkane and has no functional groups. Later on in the book, not in chapter 4, but in other chapters, we'll learn how to name compounds with OH groups. They'll end in -al for alcohol. Compounds with double bonds, they'll end in -ene for alkene, and so forth. So there will be different suffixes later on in the class. In this chapter, the only suffix we'll have will be ane. Okay? So 3 parts to a name. Question? They will be. The alkyl groups, we have to, because the substituents are alkyl groups. And so the naming of alkyl groups is indeed part of IUPAC nomenclature. Okay? So we've named our alkyl groups. So let's go through our 4-step process of generating an IUPAC name. So the first thing we do is we find the longest carbon chain. And it doesn't have to just go from left to right or right to left. There can be kinks in the chain. Sometimes the way molecules are drawn, the longest chain doesn't just go from left to right. Sometimes there's going to be a bend or a kink in it. Okay? So with more complicated molecules, you might have to look around bends and kinks and measure multiple chains to find the longest chain in a given molecule. So we find the longest carbon chain, and then we're going to get the name out of the table for that chain. Right? What's our longest chain in this molecule? 8. So what is the parent and the suffix part of this name? Octane. Okay. So we've already come up with the parent and the suffix. Everything else we're going to do is going to deal with the substituents, with the prefix part of the name. Okay. So step 2, we have to number the carbons in our chain in order to describe where the substituents appear. Okay. So we're going to number carbons in the longest chain to give the lowest number to the first substituent. Okay? So we could go from left to right or right to left. It doesn't matter. We could just flip the molecule 180 degrees and left would become right and right would become left. So we can't just number from left to right. What we have to do is number from the direction that gives the lowest number to the carbon that bears the first substituent we encounter. Okay? If we go from left to right, at what carbon do we encounter a substituent? Carbon 2. If we go from right to left, at what carbon do we encounter a substituent? 3. So in this case, which direction do we want to go? Left to right, exactly. Okay. Some of you who like to ask questions might wonder, this could be your question or it might be a different one. What happens if there's a tie? That was your question. See, I've taught this class long enough I can anticipate the questions. Well, we'll get to number 3 next because this is still part of number 2. If there's a tie, you apply something that is called the first point of difference. So that means that you would number the chain from the direction that gives you the lowest number to the second substituent you encounter, right? So if it's the same for the first in either direction, we'll show you an example of first point of difference. This particular molecule, would we number from the left or from the right? We number from the right because we encounter the first substituent at carbon 2 in either direction, but the second substituent's on carbon 3 if we go from the right. It would be on carbon 4 if we went from the left. So we go 1, 2, 3, 4, 5, 6, going from the right in this case. Okay? There's yet another question that could come up. That is, what if there's a tie? What if there's no way to distinguish? It actually does matter. What you do is you would alphabetize. So you would use the alphabet, meaning that you would number from the direction that gives the lowest number to the substituent that comes first in the alphabet. So ethyl comes before methyl in the alphabet, for example. Okay? If there was a tie on that, it wouldn't matter. But anyway, okay? So these are the ways we decide which direction to number from. And this is the IUPAC alphabet, which is not the same as the regular alphabet you've learned, as I'll tell you in a moment. Okay. Any questions on numbering? Yes, please. That would be the same. So in this case, you could go 1, 2, 3, and it would be the same. That's exactly right. Okay? All right. So our third point, third step, name and number the substituents. And we use prefixes. If we have more than one of a certain type of substituent, we would use di, tri, tetra. These are prefixes that we would use when we have multiple numbers of the same substituent. Okay? So what types of substituents do we have here? Okay, so we're going to have an ethyl group. And what carbon is our ethyl group on? 5. So we'll call that 5-ethyl. And then we have 2 methyl groups. So we've got to use di. What carbons are the methyl groups on? 2 and 6. So 2, 6 dimethyl. Okay? Any questions on how we generated those names? Okay, so now we have to put the name together. To put the name together, we alphabetize using what I like to call the IUPAC alphabet, which means we ignore all prefixes except iso. Okay, don't blame me. Once again, I didn't create this. I don't know why they decided to include iso and not sec or tert. So in the IUPAC alphabet, sec-butyl starts with B. Tert-butyl starts with B. Isobutyl starts with I. Okay, that's how the IUPAC alphabet works. The IUPAC alphabet ignores di, tri, tetra, so dimethyl starts with M. Okay, so which prefix comes first in the IUPAC alphabet, ethyl or dimethyl? Ethyl comes first. So the name of this compound is 5-ethyl 2,6-dimethyl octane. Questions on how we came up with that name? Yes. Yes, thank you. I'm glad you mentioned that. So this is something I forgot to mention when we find the longest chain. If there's 2 choices, here there were 2 choices, but they were the same. You could go 1, 2, 3, 1, 2, 3, and that's the same. But you might have 2 different chains, and you choose the one with more substituents. Yes, that is a rule. We'll do an example. I have an example. We won't get to that until Wednesday, but we have an example that shows that. Many of these minute points are best shown through examples. We'll do a couple quick examples here before we go that will illustrate some of the points we've talked about. Some of these molecules end up with interesting shapes. This kind of looks like a dog or a horse with a long body on it, but it's actually an organic compound. What is our parent name? Okay, so, and the suffix will be octane, okay? So this is octane. Do we number it from the left or from the right? Okay, some people say left, some people say right. I say right. Why? Where's the second substituent? You have 2 substituents on carbon 2 if you go from the right. So the first and the second substituent are on carbon 2 if you go from the right. If you go from the left, the second substituent's on carbon 3. So this is a good example of the point of difference rule and how it applies in a more challenging case. So having the second substituent, having 2 substituents on the same carbon counts both as number 1 and number 2. Okay? So what is our prefix here? What kind of groups do we have and how many? 5 methyls. Okay, so pentamethyl. What numbers go in front? Right. we have to use 2 of the same number to show that we have 2 of our groups on that same carbon. So 22667. 22667 pentamethyl octane. Questions? All right, let's do one more. This one's quick. Won't take us much time. Parent name, hexane. Which direction do we number from, left or right? Left, why? Alphabet. So if we go from the left, we hit ethyl on carbon 3. If we go from the right, we hit methyl on carbon 3. So here's where we use that alphabet rule to go from the left, and we call this 3-ethyl 4-methyl. I didn't give myself enough room. Methyl hexane. Any questions? All right, we'll stop there, and we'll do some nomenclature with cycloalkanes, and then we'll get into conformational analysis on Wednesday.